Hello, welcome back to another section of pre-calculus. Today we're going to be talking about the intersections of polar graphs. So this is assuming that you already learned how to graph the polar equations that we've introduced so far, the limit-zone, the limit-scat, the rose petal, and the conic section. So this is now looking at how do we find the intersections between them. So here I'm going to have two examples that we can look at together, and hopefully by the end of it, you'll be able to pick this up and do it on your own. Now, in the first example, I'm going to ask to find the intersections between the two graphs right here. R is equal to 1 plus cosine theta, and R is equal to negative sine of theta. And you'll note that I actually have the graph on the right-hand side, and they're color-coded by blue and also red. So if I'm trying to find the intersection, well, first I want to graph them to see what they actually looks like, and then that way it'll give me an idea as to where the intersections are going to be. And if you look a little bit closely on the graph on the right-hand side, you'll notice that there are two places. One of them is going to be at the pole, and then the other one is going to be at 270 degrees and at a certain radius. And by the way, for this graph, I made it so that the radius of 5 is, I made it so that the ratio is of 1 to 5. So you can see that at 10, that's actually a 2, and then at 5, that's actually equal to 1. So let me go ahead and put that in there just in case then. So this is a 1, and then this is going to be a 2. Now, as I said, the intersection is going to be at 2 points, but I need to know what the coordinates are in polar coordinates. So that's what we need to figure out. So it's not sufficient enough for me to say that, oh, it's going to be at the pole because, well, what is the angle that is at the pole? And also, what is the radius that's at 270 degrees? So let's go ahead and try to solve for this then. So let's see, thinking about how we're going to be doing this in algebraically back in algebra, we usually set the two equations to equal to each other and try to solve for theta and r. So that's what I'll go ahead and do first. So 1 plus cosine of theta is then equal to negative sine of theta. Now, thinking also back to how do we solve for the system of equation, we have a few options that we can choose. One option is to divide the other side by sine and then probably use like a trig identity, which I'm thinking most of you guys probably won't remember because it's tangent of theta over 2, to be a substitution. And while that is something that's nice and simple, we actually want to avoid that. And the reason is whenever we divide by a trig function or whenever we divide by a variable, we're going to end up losing solutions. So to remedy that, what we're going to do is we're going to go ahead and square both sides, because the result is that when we multiply by variable, we gain solutions, whereas when we divide by variables, we lose solution. And I'd rather gain than lose because we can always go back and check for those solutions then. So as I said, we're going to go ahead and square both sides. So that's going to be our first step then. So this part is going to be squared and this part is going to be squared. So let's see, the left-hand side, that will give us 1 plus 2 cosine of theta and then plus cosine squared of theta. Now that is going to be then equal to sine squared of theta. Everything is equal to in terms of cosine on the left-hand side, and I don't like the sine of theta. So why don't we go ahead and make an identity substitution? The sine of theta, we can go, sine squared of theta, we can go ahead and replace that with 1 minus cosine squared. And now everything is in terms of cosine, which is something that will be ideal then, because you'll notice what we have is then something that's quadratic. So the ones are going to be canceling out with each other. And everything I'm going to go ahead and put on the left-hand side because, again, I see cosine square theta, so that tells me that I am going to have a quadratic, so therefore I should be factoring. So 2 cosine squared theta, because the cosine 2 theta, the cosine squared theta plus the cosine squared theta makes 2 of them. Then we have the plus 2 cosine of theta, and all that is then equal to 0. Factor out what they have in common, which is going to be 2 cosine of theta, and what's left in here is going to be just a plain old cosine of theta and plus 1, and that's equal to 0. So now by the 0 factor property, I can solve for theta for each one. So 2 cosine of theta is equal to 0, or we have cosine of theta is equal to, cosine of theta plus 1 is equal to 0. So let's see, cosine of theta is equal to 0. Where is that located? I'm looking at theta being, let's see, there's 90 degrees right? And then there is 270 degrees, and then there is 450 degrees, and so on and so on and so on. So in short, what we can say that it's going to be 90 degrees and then plus 180 n for a general solution. Whereas for the other one, we have cosine of theta is equal to -1. So that is going to be cosine of theta equal to -1. So theta is equal to 180 degrees. And that's the only place where cosine is equal to -1. So we say plus 360 n in this case. All right, so let's see. Let's go ahead and now limit what we have, because our domain, keep in mind, is going to be from 0 to 360. Those are the only solutions that we have, or only the solutions that we want. So from here, we only want the one that's 90 degrees and also the one that's 270 degrees, okay? So keep in mind right here, let me just kind of write on the side. So the domain is going to be from 0 to 360 degrees, because that's how long it's going to take for each one of these graphs to basically go back into the same cycle. Whereas for this one, we have theta is equal to 180 degrees. And remember, for each one of these, I need to actually check the solution. And what I mean by that is to plug it back in order to figure out what r is equal to. Now, normally we would just plug it into one of the equation to figure out what r is, but because we have to check for the solution, your r values might not be the same. So what that means is you have to take each of them and plug it into each respective equation and see what you get. So let's see. Let's go ahead and plug it into the first one. So let's go ahead and denote that as blue. If I take r is equal to 1 plus cosine of theta, and I plug it into the first one where theta is equal to 90, we are going to get r, which is equal to 1 plus 0, which is equal to 1. Now, for the other one, we get r is equal to 1 plus 0, which is also equal to 1. And for this one, we get r is equal to 1 minus 1, which is equal to 0. Whereas for the other equation, we'll do exactly the same thing. So we'll go ahead and denote that as red. We said r is equal to negative sine theta. So when theta is equal to 90, we get r is equal to -1. So you can see how these two right here, they do not match. So that means that's not going to be a solution then. For the second part, when I plug in theta is equal to 270 into sine of theta negative, we're going to get negative of -1, which is equal to 1. So that means that one's okay. And finally, for 180 degrees, we're going to plug it into that one. So we get r is equal to, looks like it's -0, so it's equal to 0. So that means it's okay. So in conclusion, the 2 points of intersections are going to be as follow. So let me just go ahead and put that over here as a final answer. We have 2 points. We have looking at theta is equal to 270 degrees, where r is equal to 1. So that means it's going to be written as, I think it's like 270, and then we have 1 right here. Okay, so that's the notation for it. And for the other one, I have 180 degrees, and that radius is going to be 0 then. So those are the 2 points that you see right here. So let me just kind of match that up. So this guy right here, that's going to be this point. And this guy right here, well, that's going to be this point over here. Okay. All right. So let's try to do another example just to make sure that you can see how this all works out again. So something a little bit more complex then. Find the intersection between the two graphs right here, where r is equal to sine of theta for one equation. And that one is denoted in orange. Sorry, it's a little bit hard to see for that one. And the second one, r is equal to sine 2 theta, where the graph, as we learned, is going to be a rose petal with double the number of terms that you have in order. You basically double the value inside the coefficient that's multiplied by theta in order to give however many petals you have. So in this case, because we have 2 theta, then that means we have 4 petals total. So to bypass the first part, which is graphing, I've just, again, graphed it on the right-hand side for you, so you can kind of take a look at that. And you'll notice that there are definitely a few intersections over here in this case. And I am going to go ahead and pull them out. So I see definitely the pool being one of them. Another one is in quadrant 1 over here, and another one is in quadrant 2 over here. And I think that's going to be all of them. So we're basically expecting around like 3 of them, basically. Now, do they actually match at the same values? I don't know, so we're going to try to figure that out. So again, just like before, what we're going to do is we're going to go ahead and take the two equations and set them equal to each other. So sine of theta is equal to sine of 2 theta. And thinking back to last semester where you saw for trig identities, then what I want to do now is change the sine 2 theta by its identity, which is going to be 2 sine theta multiplied by cosine theta. Okay, so that's going to be equal to sine of theta. Now, remember what I said earlier for the previous problem, okay? Try not to divide by a variable if you can, because otherwise you're going to lose the solution. In fact, here, let me just kind of write that as a note, okay? Do not divide by a variable, okay? Because you will lose solutions. Okay, so that's what we always try to avoid if possible. So what that means is I don't actually want to divide by sine of theta because yes, that would give me something nice and simple, but we're going to lose some solutions there. So the way to remedy that is, again, thinking about quadratic, what we did earlier, we're going to try to set one side equal to 0 by moving the sine of theta onto the other side. So 0 is equal to 2 sine theta cosine theta minus sine of theta. So I'm just basically subtracting sine of theta to the other side then. And again, just like before, we're going to go ahead and factor out what they have in common. So 0 is equal to sine of theta multiplied by 2 multiplied by cosine of theta minus 1. And you can see now we can actually solve for both of these right here, right? And earlier, as I said, if you actually divide through by sine of theta from the very get-go right here, you are going to lose out that solution where sine of theta is equal to 0. And I don't want to do that then. Okay, so let's go ahead and isolate them by the 0 factor property. Sine of theta is equal to 0. And 2 cosine of theta minus 1 is equal to 0. Solve for each one. The first case, I'm looking at sine is equal to 0. So that means that theta is equal to everything that's on the x-axis. So 0 degree, 180 degrees, 360 degrees. So in short, it's kind of like saying 180n. So that's the general solution then. Whereas for the second equation, that gives me something simple as cosine of theta is equal to 1/2. And so where that's located, let's see, cosine is equal to 1/2, that's going to be at 60 degrees. There are actually quite a few of these then. So in quadrant 1, right, we have theta is equal to 60 degrees. And we also have in quadrant 4, right, where theta would then be equal to negative 60 degrees. And for each one of these, we're going to say plus 360n because we're looking for a general solution. Now, once again, going back to the very beginning and thinking about the domain, right? How long does it take for each graph to repeat itself? And the domain in this case, again, it's 360 degrees. It's just like a regular trig function in that case then. So what I need to do is I need to select values of n for each one of these general equations. So then that way I can figure out where my solutions are within 0 to 360. So in the first case over here, we're going to go ahead and select n is equal to 0, which is going to give us theta is equal to 0 degrees. So that's one solution. N is equal to 1, so theta is equal to 180 degrees. And then n is equal to 2, so theta is equal to 360 degrees. Now for the second one, same idea, right? So all these, again, remember, all of these values of theta, they are within 0 to 360 degrees because the domain is supposed to be from 0 to 360 degrees for both of them. So in, let's see, the one in quadrant 1, there is just theta is equal to 60. So that's pretty much the only one there. Whereas for the second one in Q4, I'm going to go ahead and select n is equal to 1 in this case. So in the first case, I had, and let me just kind of erase this so I can kind of show the work over here. Okay, so back up just a little bit. So for the one in Q1, right, we say let n equal to 0. So that's how we get theta is equal to 60 degrees. The one in Q4, right, we're going to go ahead and let n equal to, looks like it's 1, so theta is equal to 300 degrees. Okay, keep going for each one. Solve for r for each one of these cases. And this one, now, unlike the first problem where you had to go back and check your work, this one I actually don't have to go back and check my work. And the reason for that is I didn't square both sides. I didn't multiply both sides by any variables. So in short, I didn't create any extra solutions. So that's why we can just go ahead and plug in and solve for r, and then we're pretty much done. So we'll just take one of those and solve for r, and then yeah, and then just plug in for each one of those then. So let's see here. Let's go ahead and use the easier one. R is equal to sine of theta, and we're going to go ahead and substitute for each one again. Again, remember what I said. I didn't square both sides, or I didn't multiply both sides by variables, and that's why I don't have to check for extra solutions. Okay, so that's why we can just plug in one simple equation. So the first one, when theta is equal to 0, r is equal to 0. When theta is equal to 180, you have r is equal to 0 once again. And then when theta is equal to 360, that's r is equal to 0 once again. So those are pretty direct. And let's see, the one that's in quadrant 1, when theta is equal to 0, then r is equal to root 3 over 2. And then when theta is equal to 300 degrees, r is going to be negative root 3 over 2. So these are all of my solutions then. We have 0, 0 degrees. We have 0, 180 degrees. And then we also have 0, 360 degrees. So what that means is you're going to actually intersect at the pole 3 times, because every time you go to those degrees, you're going to go back to the pole for both of the graphs. And that happens quite often then. In addition to that, we also have 2 other points that are not the pole. We also have when r is equal to root 3 over 2, we have 60 degrees. And then when we have whenever we have radius is equal to negative root 3 over 2, then we have 300 degrees then. So in comparison to our graph, hopefully you can kind of see where they're located. Remember, earlier we said that we have 3 places, right? We have the one in quadrant 2, we have the one in quadrant 1, and we have the pole right there. So those are going to be our solutions then. So yes, technically, physically, there are 3 intersection points, but then there are a total of 5 intersections because you enter the pole, or you intersect at the pole 3 times. Okay, so whenever you do this, you have to actually show every single time that it goes to the pole, because later on we're going to be doing something called parametric equation, which all of this actually matters, and you're going to definitely see that in calculus next year. All right, so thank you again for watching. I will see you next time.